In particle physics, a generation is a division of the elementary particles. Between generations, particles differ by their quantum number and mass, but their interactions are identical. There are 3 generations according to the standard model of particle physics. Each generation is divided into 2 types of leptons and 2 types of quarks. The 2 leptons may be classified into one with electric charge -1 and one neutral. The 2 quarks may be classified into one with charge -1/3 and one with charge +2/3. Overview. Each member of a higher generation has greater mass than the corresponding particle of the previous generation, with the possible exception of the neutrinos. For example, the first generation electron has a mass of only 69995110000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 106 MeV, C2, and the third generation tau has a mass of 7003177770000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 This mass hierarchy causes particles of higher generations to decay to the first generation, which explains why everyday matter is made of particles from the first generation. Electrons surround a nucleus made of protons and neutrons, which contain up and down quarks. The second and third generations of charged particles do not occur in normal matter and are only seen in extremely high-energy environments such as cosmic rays or particle accelerators. The term generation was first introduced by Haim Harari and Les Houch's Summer School, 1976. Neutrinos of all generations stream throughout the universe but rarely interact with normal matter. It is hoped that a comprehensive understanding of the relationship between the generations of the leptons may eventually explain the ratio of masses of the fundamental particles, and shed further light on the nature of mass generally, from a quantum perspective. Fourth generation. Fourth and further generations are considered to be unlikely. Some of the arguments against the possibility of a fourth generation are based on the subtle modifications of precision electroweak observables that extra generations would induce. Such modifications are strongly disfavored by measurements. Furthermore, a fourth generation with a light neutrino has been ruled out by measurements of the widths of the Z boson at CERN's Large Electron Positron Collider. Nonetheless, searches at high-energy colliders for particles from a fourth generation continue, but as yet no evidence has been observed. In such searches, fourth-generation particles are denoted by the same symbols as third-generation ones with an added prime. According to the results of the statistical analysis by researchers from CERN and Humboldt University of Berlin, the existence of further fermions can be excluded with a probability of 99.99999%. The researchers combined latest data collected by the particle accelerators LHC and Tevatron with many known measurements results relating to particles, such as the Z boson or the top quark. The most important data used for this analysis come from the discovery of the Higgs particle. In the Standard Model, the Higgs particle gives all other particles their mass. As additional fermions were not detected directly in accelerator experiments, they have to be heavier than the fermions known so far. Hence, these fermions would also interact with the Higgs particle more strongly. This interaction would have modified the properties of the Higgs particle such that this particle would not have been detected.